Alrighty, we got a test coming up in section 6.2, right triangle trig, and let's go over these practice problems to see if we're ready for the test. Always read the directions. Number 1, find the exact value of the 6 trig ratios of angle theta. So we got to think back to, well, first, we got to find the missing hypotenuse first. Let's start there. We got the legs, we're missing the hypotenuse, which is across from the right angle. So we got to go back to my buddy Pythagorean, a squared plus b squared equals c squared, and c is the hypotenuse. So that's what we're looking for. So our legs are 4 and 5. Oops. 4 squared plus 5 squared equals c squared. And let's see, 4 squared is 16, 5 squared is 25. So if we add those up, we get 41. That is c squared. Oops. And we square root. C is the root of 41. That's our hypotenuse. So our answers are going to have some radicals in them. And it does say find the exact value. You know, we could punch 41 into the calculator and take the square root of it and put a decimal there, but decimals are not exact. They're rounded off. So the directions say stick to those exact values. Now we got to think of Sohcahtoa. Some old hippie came a-hoppin' through our apartment. Sohcahtoa, sine is opposite over hypotenuse. So to find the sine of angle theta, we look across from it. Opposite is 4. Hypotenuse is root 41. Opposite over hypotenuse. And we are going to rationalize that. But before we do, let's find the reciprocal of sine, which is cosecant. If we want cosecant, we just flip sine over, so that's the root of 41 over 4, and now we don't need to rationalize. But when we do rationalize for sine theta, we're going to multiply the top and the bottom by that denominator radical, the root 41. And we're going to get 4 roots of 41 over 41. And here we cannot reduce. You know, those numbers don't have any common factors. Under the radical, 41, we can't simplify that down any farther, so we'll leave it just like that. Where the hippie come a-hoppin', or the hippie came a-hoppin', cosine is adjacent over hypotenuse. So from angle theta's perspective, adjacent 5, hypotenuse is root 41. And let's get the reciprocal of that. You know, we got our sine, cosine. Next we're going to find tan, and then we'll have cotan, secant, cosecant. So if we flip over cosine, we get the secant of theta, which is going to be the root of 41 over 5. And back to cosine, we will rationalize that denominator and get 5 roots of 41 over 41. Again, 5 and 41, we cannot reduce there any farther. Last, tangent, opposite over adjacent through our apartment. Opposite's 4, adjacent's 5, so it's just 4/5. And we flip that over for cotan, 5/4. There are these 6 trig ratios of angle theta, all to the exact value. Here, 2 through 5, it says use a calculator to evaluate each function. Round your answer to 4 decimal places. Be sure the calculator is in the correct angle mode. I forgot to pencil it in here, but you are going to have, those are degrees. And we see our radians below are in terms of pi. So let's see, we want the tan at 41. That should be easy enough. 41, hit the tan key. 0.8692, we'll round that 2 up because this number is higher than 5. So 8693. 0.8693. Alright, cosecant of 7. There is not a cosecant button on our calculator, but we know that cosecant is 1 over sine. So if we find the sine of 7 degrees and flip it over, we'll have our cosecant. So the sine is 7. 7, we'll hit the sine key. Now we want to flip that over. A calculator should have a 1 over x key or x to the negative 1 key. I'm looking for it here on my computer. Oh, there it is, 1 over x. So I'm going to flip that over, and we get 8.2055. That's a 0, so we'll leave that rounded as a 5. 8.2055. 2055. Make sure I got that right. Yep. And we were in degree mode. Now the next 2 questions are in radians. We can, that the dead giveaway is the pi there. So we'll now put our calculator into radian mode. We'll clear this out. There we go. We want the tan of pi over 16. So we're going to do pi divided by 16 and then hit the tan key. So pi divided by 16 equals and then we'll hit tangent. Let's see here, 1989. 1989. And the last one we have here is cotan of pi over 16. But remember, tan and cotan are reciprocals. So we're going to do 1 over the tan of pi over 16, which we just found above. And you know, there's our calculator. Our answer is still in our calculator. So to find that reciprocal, I just do the 1 over x. Boom. We got it at 5.0273. 5.0273. And double check that again. 0273. Yeah, that next number was a 3, so we round it down, leave it alone at a 3 at the end there. Critical thing there is the mode, radians or degrees. Be careful. Let's see. Now we're going to evaluate these trig functions given our special angles. Don't use a calculator. Use the table. We want the exact value. You know, we could find this on the calculator and round it off, but that is not the exact value. So here we want the cosecant of 60. If we look on our table, we have 60-degree angles, but there is no cosecant. But we know that cosecant is 1 over sine, the reciprocal of sine. So if we look up the sine of 60 and flip it over, we'll have our answer. Here is sine of 60, root 3 over 2, so we're just going to turn that over. If we have 1 over root 3 over 2, you know, we invert and multiply by the reciprocal, so that would be 1 over 1 times 2 over the root of 3. So we have 2 over root 3, and we want to rationalize the denominator. So we're going to multiply the top and the bottom by that denominator's radical. And up top we're going to have 2 times the root of 3. And below that, root 3 times root 3 is root 9, and that square root is 3. So there's our exact value for cosecant. Tan of 30 we can get right off the table. Here's tangent of 30, root 3 over 3. Now I think for the last two here we're solving right triangles. Or no, we got a number 10. It's a different type of problem. So here's our first scenario. This is actually the one I like better. I think it's easier. We have two sides of a right triangle, and we want to find all the missing stuff, the missing side and the missing acute angles. So the easiest thing to find first is the hypotenuse. Pythagorean theorem, a squared plus b squared equals c squared. So our legs are 14 and 15. We're going to square them and add them up, and that's going to be equal to c squared. And let's see here. We have, 14 squared. Oops, I hit the cube button. 14 squared is 196. And 15 squared is 225. So if I take my 196 and add 225, I get 421, and I'm going to square root that for my hypotenuse. And this time we'll take this as a decimal. So we're going to have 20.5. We'll round it off to one decimal. 20.5 is our missing hypotenuse. C equals 20.5. Let's just see if that answer made sense, and if I maybe pushed a button wrong on the calculator. Out of the three sides of a right triangle, which side is always the longest? Well, it's going to be the hypotenuse, or in a general triangle, the angle across, or the side across from the biggest angle. In a right triangle, the biggest angle is the right angle, so the biggest side will be across from it, and that makes sense. Our legs are 14 and 15. The hypotenuse is more than that. So we have all three sides of the triangle. Now we're going to find angle A, and we're going to find angle B, and we can choose any angle first, and we can use any trig function we want. So let's see here. You know, the one we found ourselves and we rounded off was this 20.5. To get the best, most accurate answer, let's use the legs that they gave us. So here from angle A, if I look at 14, that's the opposite side. 15 is the adjacent side. That means we're going to use tangent to find that. The tan of angle A is going to equal 14 over 15. Now before we solve this, you could use any trig function you wanted. We could found the sine of A. The sine of angle A would be opposite over hypotenuse, 14 over 20.5. We could have found the cosine of angle A. Cosine would be adjacent over hypotenuse, 15 over 20.5. You know, all of these will give a very similar answer. Since we rounded that hypotenuse off when we solved for it, it will be a little less accurate than the tangent that we're using. But these would give acceptable answers for the test. And we want to solve this for the angle. How do we get rid of tangent? We use the tan inverse. Like squares and square roots, they cancel each other out. So we're left with angle A is equal to the tangent inverse of our fraction 14/15. So to solve this on the calculator, we want to divide the fraction first, 14 divided by 15. Make sure you hit equals, and then that's our fraction. We want to do the tan inverse of that fraction. So we're going to do, we want to be in degree mode. We're going to do inverse. That turn our tan to the -1, and that gives us 43.025. Let's take it to the 1 decimal place, so that would even leave it at 0. 43 degrees. Angle A equals 43 degrees. And let's even write it in there. Now the easiest way to go would be, we have the right angle and we have the 43-degree angle. We could subtract those from 180 and find the missing angle B. But maybe we made a mistake and maybe this angle A is incorrect. If we solve for B with a trig function and we get that one right, we might find there was a mistake with angle A. So let's play it safe and go to angle B and find its value with trig functions. Again, the two sides we were given are the opposite side and the adjacent side from angle B. But now for angle B, if we do the tan of angle B, that's going to be the opposite side 15 over 14. Look what we had up above here. This was the tan of A was 14 over 15. Now it's B is 15 over 14. We just flipped it over. And our process is going to be the same. We will take the tan inverse of both sides of this equation. Tan and tan inverse cancel. Angle B is the tangent inverse of 15/14. So 15 divided by 14 equals, there's our fraction, and we want to do inverse tangent. 46.97, we can round that up to 47. So 47 degrees. And now we can do a little check on our work here. Angle A and B should add up to 90, since angle C is a right angle. And if we add those, we do get 90 degrees. So that's just another check to make sure we probably did everything right here. And we have solved the triangle. Every angle is known, every side length is found. Okay, number 9 here, same scenario, but now we have one angle and one side. We're missing two sides and one angle. And we want to find everything that's missing. Pythagoras gave us the missing side here to start because we had the two legs of the right triangle. Now we have two angles of this triangle, so we can find angle B right off the bat. We can just do 90 degrees minus the acute angle that we know is 37, and that would leave us 53 degrees for angle B. All right. Now we want to solve for the missing sides. Let's call this side A because it's across from angle A. Over here is our hypotenuse. Let's call that C. So let's see here. We have some options, a few different options, but not everything's available. If I'm looking here at this angle 37, if I want to solve for side A first, the side that I want to find is opposite the angle, and I have adjacent. So opposite and adjacent are what I have and what I want. So what trig function deals with opposite and adjacent? That would be tangent. I could set up my equation to say the tangent of 37 degrees is equal to A over 12. Is there any other way I could do that? Not yet. We could have went from the 53-degree angles perspective. From the 53-degree angle, the side we have is opposite, and the side we want is adjacent, so that would also be tangent. We could set up the tangent of 53 degrees is equal to 12 over A. We saw something just like that in the last problem we did. Either of those would give us the right answer. Let's go with the first one. So to solve this for A, this is the easy one. Our denominator is a number, so we're just going to multiply both sides by this denominator 12. And we're going to have 12 times the tangent of 37 is equal to A. And of course, we want to do this inner stuff first. We want to do that trig function on the calculator first. So 37 degrees and hit the tangent. We are in degree mode. 37, hit the tan key. There's our tangent of 37. We're going to want to take that and multiply by 12 times 12. And we get our answer, 9.04. Again, let's take this to 1 decimal place, so just 9. 9 will work just fine. So side A is 9. And let's even, I'll just write over top of it, That's now a 9. Now that we have that, we can use that in other trig functions to solve for the missing hypotenuse. And maybe even the easiest way to go for that hypotenuse would be a Pythagorean theorem. 9 squared plus 12 squared equals c squared. But let's try a trig function just to see how it works out. Let's go from the 37-degree angle's perspective. Now we have two sides, and we want the hypotenuse. So if we think back to our Sohcahtoa, the hypotenuse is something we want, and the only two trig functions with hypotenuse are sine and cosine. So we could probably use either of those from either angle, the 37 or the 53. If we went from the 33-degree angle, or 37-degree angle, we could do the sine of 37, and that would equal opposite over hypotenuse, 9 over c. From the same 37-degree angle, we could do the sine of 37, we could do the cosine of 37. The cosine of 37 would be adjacent over hypotenuse, 12 over c. Either way, we have c as our denominator. The numerators are different because of the different trig functions, sine and cosine. So either one of those would work. I'll just stick with sine. Remember, we want to get c alone. We did a shortcut. You remember in class we would here multiply both sides by c. So if I multiply this side by c and this side by c, those are going to cancel. And we're left with 9 equals this. And then we would divide both sides by the sine of 37. So c would equal 9 divided by the sine of 37. We're back to the original problem. We could just switch the c and the sine of 37. So off to the calculator. We want to do 9 divided by 37 sine. 37 sine equals 14.95. If we're rounding that off to the 10th place, we'll round that up to 0 there, and that'll just be a nice even 15. So c is approximately 15. Does that make sense for our triangle? We could always check that with a little Pythagorean theorem. Why not? 9 squared plus 12 squared, does that equal, we don't know, 15 squared? Well, 9 squared is 81, 12 squared is 144, 15 squared is 225. So if we do add these two together, yes, we do get 225. And now that I think about it, if we think back to the original problem here, this is a 3, 4, 5 triangle, or a multiple of it. If we divide all sides by 3, this divided by 3 is 3. This divided by 3 is 4. This divided by 3 would be 5. That is a 3, 4, 5 right triangle. Alright, last one. Pythagorean identity here from our trig function. Sine squared plus cos squared equals 1. We have cos is a quarter, so we're going to plug that into our formula. Sine squared of theta plus cosine. Cosine is 1/4, and that's squared. That equals 1. Well, let's square that 1/4. Sine squared of theta equals 1/4 times 1/4 is 1/16. And let's rewrite this with a common denominator. Easy way to write 1 would be 16/16. And now we can subtract a 16th from each side. So the sine squared of theta equals, subtract this, and we get 16/16 minus 1/16 is 15/16. And to get rid of the squared, we square root both sides. Numerator and denominator can be done separately. So the sine of angle theta is equal to the root of 15 over the square root of 16 is 4. Can we simplify the root of 15 at all? Is there a perfect square hidden in there? No. So that's it. There's our value of sine. And they didn't ask us for it, but let's just have a little more fun. And what if they said find tangent also? The tan of theta. Well, we have sine. We found it. We have cosine. Tangent is sine divided by cosine. Tangent is sine divided by cosine. So if we plug sine in the numerator, the root of 15 over 4, and we divide that by cosine, which was 1/4, we have a fraction divided by a fraction. To divide those, we invert and multiply. So our numerator will stay the 15 square rooted over 4, and we're going to multiply that by 4 over 1 when we flip this. 4 over 1, the 4's cancel, and we're left with the square root of 15. Tan of theta would be the square root of 15.